Okay, in this lecture we're going to cover homogeneous higher order differential equations that have constant coefficients. So the previous equation we used just an Euler equation as an example of a higher order differential equation. In this example, in this lecture, we're going to look at constant coefficients. So here's our differential equation where y to the n represents the nth derivative of y. And then our a's with our subscripts represent the coefficients, and you'll notice they are constants. You also notice this is homogeneous because it's equal to 0. And basically we're going to use the same approach here that we used for second order differential equations. We're just going to assume a solution of y is equal to e to the lambda x. And when we do that, we'll find the characteristic equation. Some versions of the textbook, this equation is incorrect. So I have corrected it here in this lecture so that we will have the correct polynomial. So when you substitute e to the lambda x for y, you're going to be taking its derivative on these higher order terms. And so if we have the nth derivative of y, then we'll take the derivative of this equation n times, meaning we'll get a coefficient of lambda to the n. And so what's written here is the characteristic equation, just like what we did with a second order differential equation, where the e to the lambda x term returns with each derivative, and we basically factored it out and forced the coefficient terms to sum to 0. So this is our characteristic equation. It's just a higher order equation in lambda. And so we'll have n roots to this equation and n basis set solutions for y. So in general, the solution depends on the roots of the characteristic equation, and as we've shown before, we can use MATLAB or some similar computational program to find those roots. And when you have a higher than a quadratic, you have several different possibilities for your roots. So first of all, you can have just a simple distinct real solution. Complex solutions always come in pairs. So you could have a complex conjugate pair. You could have multiple real roots or multiple complex conjugate pairs. And they can be the same or different. So for example, we could have a double complex conjugate root, meaning we would have an equation to the fourth power, and it would have a double root that was a complex conjugate pair. So things get a little more complicated because you can have double roots. It's really unusual to have differential equations higher than third order that represent most physically modeled systems, but not completely so. So we'll talk a little later in the course about some possible circuits problems that might have higher order roots, but usually third or fourth order is about as high as you would go. So if you have distinct real roots, that would be our first case. Then that just means you would have lambda would be a real number, and so you would get a basis set of solutions that would look like e to the lambda x. And here's your general equation for y. It's just going to be the sum of all of these. Simple complex roots would occur in complex conjugate pairs, so you would have a real part and then plus or minus an imaginary part. And so you can show, and we won't show in this particular lecture, but you can show that if you substitute e to the lambda x, where lambda is this complex conjugate pair, that basically that's the two linearly independent solutions are an exponentially multiplied cosine function of frequency omega and an exponentially multiplied sine function of frequency omega. And in most real-world engineering systems problems, lambda is going to be negative, and so this ends up being an exponentially damped sine and cosine. Otherwise, this is an unstable exponential growth problem, which in most physical systems does not commonly occur. So it's a sinusoidal, it's a damped sinusoidal solution with a cosine term and a sine term. So here is an example of a problem, an initial value problem that's going to have simple complex roots. So this is a third order differential equation. And so we're going to have three boundary conditions, one on y prime, and one on y double prime, all at x equals 0. So when we substitute e to the lambda x and take its derivatives and get a characteristic equation, this is the characteristic equation that we get. Once again, to me, it's never intuitively obvious that that it has a root 1. You can actually find that by grouping. So if you group these first two terms and you group these second two terms, then what you have is, if you factor out a lambda squared from the first two and you factor out a 100 from the second two, you can have a lambda squared plus 100 times lambda minus 1. And so there, maybe it's obvious that that root is 1. And then you can show that the other two roots are plus and minus 10i. You can also do this by taking a simple MATLAB program and solving for the roots. So you get a general solution in its derivatives that looks like this. So y is just going to be this c1 e to the x, where lambda here is 1. And then you have our sine and cosine terms, and the reason that this is not a damped sine and cosine is that usually this would be a complex conjugate that would have a real part. In this particular example, the real part is 0. So this is multiplied by e to the 0x, which is just 1. So you get the cosine and the sine, but the exponential damping term simplifies to 1. If you take the first derivative of this, you get y prime. And of course, the first term is unchanged. The second term, cosine goes to sine goes to cosine, and then you take its derivative again, you get this second derivative term. So once again, y is our general solution. Y prime and y double prime are its first and second derivatives. The reason we're doing that is so that we can substitute our initial values and solve for a, b, and c1. So in doing that, first of all, if we set x equal to 0, those three equations become the following. So we get c1 plus a is 4, we get c1 plus 10b is 11, and we get c1 minus 100a is minus 299. The terms on the right come from the initial values given at the beginning of the problem. The terms on the left come from taking those three previous equations for y and its first two derivatives and substituting x equals 0 into those equations. So now we have three equations and three unknowns, and we can solve for a, b, and c1, giving us a equal 3, c1 equal 1, and b equals 1. So if we substitute that into the equation for y, then this gives us our particular solution. In this particular case, we have this e to the x, which is a positive exponential, and added to that is this sinusoid. So this sinusoidally oscillating curve just follows this exponential track. This is an example of a system that would be physically unstable. If this occurred in the real world, you would have some cataclysmic event that would happen out here. If this was oscillation of a bridge, obviously it would rupture. If this were exponential growth of a bacterial colony, obviously at some point it runs out of food and saturates. So this is not a curve that can be sustained through infinity. Okay, the other case is multiple real roots. So in this case, you would get lambda as a root, but you would get a multiple root. So like an example would be if you had lambda minus 4, lambda squared minus 4 is equal to 0, then you would get a double root at 2. I'm sorry, lambda minus 4 quantity squared, you would get a double root at 4. So if you have a perfect square for your polynomial, you're going to get a double root. If you have a perfect cube, you're going to get a triple root, and so on. So what that means is e to the lambda x is a solution, and we're going to use what's called our modification rule. So for every order of root you have an additional basis solution that is multiplied by x. So if we have an mth order root, so we have lambda as a repeated root m times, then we'll have an e to the lambda x, we'll have an x e to the lambda x, we'll have an x squared e to the lambda x, and so on, all the way up to x to the m minus 1 e to the lambda x. And these multiplications by a power of x have to be included as a potential solution because we do have this, this higher order root. So this can also occur when you have complex conjugate pairs, and in that case we call these multiple complex roots. This means a complex conjugate pair forms a double root of the characteristic equation. You almost never have a triple root in a complex conjugate pair, so that would be highly unlikely. So we're just looking at what we do when we have a double root. So notice here's our e to the gamma x and our constant and our cosine and our other constant and our sine. But now notice because the root's a double root, we have this second term added. So we have this a2x and this b2x. So this is our modification rule for higher order roots being applied when we have a higher order complex conjugate pair. And you notice that that doesn't affect the damping part, the e to the gamma x. It only affects the sinusoidal part. Okay, we're going to conclude this lecture video here, and then we will talk a little bit more about some other things in inhomogeneous differential equations. So if you want to stop the video here, you can. This is just going to be a very short addition to the video where we'll talk about a couple things in inhomogeneous equations. So rather than start a new video, if you want to pause the video here, or you can continue watching, but this is a new topic. In general, an inhomogeneous higher order differential equation takes the form where we have a term on the right hand side that's a function of x. And in that case, we have a solution that consists of a homogeneous part and a non-homogeneous part. The homogeneous part is the solution to the homogeneous differential equation. So in other words, if I come in here and I set r of x equal to 0 and solve the differential equation, I get this homogeneous part. Now, then I need to go in and figure out what the contribution of the inhomogeneous part of the equation is, and that's what's referred to as the particular solution. So once again, I want to emphasize that when dealing with a non-homogeneous equation, the term particular means something different. It means, in this case, the solution to the inhomogeneous part of the equation. So, for example, an initial value problem would now have to contain n initial conditions. That would give us all of the unknown coefficients for the homogeneous part of the equation. The particular solution comes from guessing at a solution to the inhomogeneous part of the differential equation, substituting it back into the differential equation and forcing it to work, just like we did with second order. So for a non-homogeneous equation with constant coefficients, we use the method of undetermined coefficients to find the general solution, and we'll follow exactly the same rules that we used for the second order systems. So we won't repeat that there. Let me just say that what will happen is you'll have whatever your function r of x is, you'll have a table, the same table we use for second order, that'll basically give you a menu of different possible functions based on what your Rx is. And then you choose one of those functions, the appropriate one, substitute it back into the differential equation, and you get your particular solution.